Once more, welcome to Chem 101. We're discussing about the modern atomic theory. So an atom came in the around the 5th century rather. I don't want to say early or late, but the idea began or started during the 5th century, where individuals came about, some philosophers, especially the Greek philosophers. We have Leucippus, yes, Leucippus of Miletus, and then also we have his student, yes, Democritus. Yeah, okay. So they came about this idea that matter is made up of tiny or small particles. That's why if you remember from the recent video, I said an atom comes from the Greek word atomos, comes from the Greek word atomos, which means indivisible. So the idea about an atom is that matter is made up of an indivisible particle. And this particle, they refer to it as atom. Although there were several contradictions against what their ideas or the ideology was about. But though, people still celebrated it, just like the case of Pluto, who celebrated the geocentric theory for like 1,400 years before the whole geocentric um, theory came to be. So science is about proofs, it's about facts. So if you cannot disprove it, then it has to stay as long as possible. So an atom began with this people, they started this idea. And then it grew to the stage where there were a lot of contradictions, there were a lot of people who counter, people like Aristotle, so many others. So this brought about the modern view, the modern understanding of what an atom is. Yes, in the early 19th century, yes, 1808, that's 19th century. You know how many centuries afterward? From 5 to 9, do the mathematics, that's about 14 centuries after. Yes, this man came about the theories that actually support that really matter is made up of a particle, a particle. There's something in that particle is really an atom. John Dalton, an English chemist and metrologist, he came about this in 1808. Sorry. So in the early 19th century, came about this idea that this is what I think an atom is. He gave what we call the posit. That is, he gave postulate. He gave, some agreeable terms to an extent. Let's hold it there. He gave some terms, and one of those theory, some of the terms is what we refer as the Dalton theory of an atom. So, first of all, he said an atom is the smallest indivisible particle of an element. Okay, you see, it correlates with what the early Greek philosophers were actually making reference to. Yes, the smallest indivisible particle of an element. Okay. And then the second posit he made was that, first of all, we said the smallest indivisible. The second posit is, I'm just taking you through history. Sorry, I'm not penning it down. So the second one is atoms can neither be created nor destroyed. He is beginning to give his posit, that is his theory. And then the other thing he saw was that atoms of the same element looks alike in all aspects, but are completely different from atoms of other elements. So what it means is atoms of the same element are more the same in behavior, but differ. When we say the behavior, we mean the reaction to external environment. How do they behave? Because an atom of chlorine is different, really, is different from an atom of sodium. Yes, truly. But we'll come to all of these modifications as well. So this is the third thing he saw about an atom. The fourth theory, he said, atoms, atoms combine, and they do so in simple ratio. Okay, they combine in simple ratio. Okay. The fourth of this, or the fifth, if I'm counting correctly, he said the atoms, that is all chemical changes, yeah, emanates from either the combination or the separation of atoms, which is true. I mean, chemical change, I mean, changes that are almost irreversible. That is, changes that brings about, you know, new products and cannot be reversed easily. Yes, just like you have, yes, burning of wood is a chemical change. You don't expect to burn wood to ashes, and I don't know, probably there may be different ways of returning the ashes back to wood, but this is what a chemical change can actually be. So what it means is, generally, I just give you a perspective of what we can see around. But in chemical change, we say all chemical changes have resulted to the behavior of the atom, either in combination or in separation. So this man decided to bring the idea of what we call the modern atomic theory. This is the base of the modern atomic theory. It started from, this posits. These posits were enough to give us direction. But as chemistry begins to advance, we realize that there are some other complications also. One of those complications were what resulted to the modification of these theories. Modifications in the sense that there were some which actually obeyed, but some, you know, do not obey that. So let's talk about some of these modifications. I'm just giving you a brief. This is a discussion, a brief summary of what or how the modern theory of an atom came to be. So one of the other things that resulted to changes, one of it, let's start with the first one, which is atoms are seen to be indivisible particles. This brought about contradiction when Rutherford, yes, N.S. Rutherford in 1911 came about the discovery of a nucleus, and he realized that this atoms you're talking about, that is the smallest indivisible particle, there is something in the nucleus. And that thing, with further research, it was made known that, the nucleus contains some particles. So the idea of smallest indivisible really did not count, because there are still particles which are more smaller. You understand? Because if you say something is indivisible, then that means it's the smallest. That means there's nothing. You bring a knife and you want to cut it, there's no way you can dissect it, you can divide it any longer. But that same thing you said is indivisible has something that are much more smaller than the whole thing itself, which came about the proton and the neutron in the nucleus. So it means, the nucleus can actually, can actually, the atom can actually be divided. That's just the whole idea. So this is a modification. The discovery, the later discoveries of atoms, contributions brought about clarity in that. So the second of it is this idea of atoms can either be created, not destroyed. What it means, this is common. This is common. This is what informs the basic theory, or the basic law of conservation of mass. Yes, so it works. It works for a lot of other elements in the periodic table. But elements from bismuth, yes, elements from 82, lead from 82 to 83, radioactive elements per se, you find out that it is a bit more contradicting for this radioactive element, because uh, they tend to form what we call uh, daughter cells. Let me not be directed to biology. I know you hear about this a lot in biology, but what I mean is that this radioactive active element can actually disintegrate to form new forms of, nucleus, new forms of elements, new, completely different. That means one of these atoms can really be destroyed to form new ones. So you see the case of uranium 236 undergoing what we call an alpha decay, uranium 236. So 36, 92, and then to give you Korean, which is to right off left, which is 232 and 90 plus H E 42 plus energy release. So this is a typical example of what we call the nuclear fission in chemistry. When you hear fission, it means splitting. Okay? When you hear fusion, it means fusing. You understand? Fusing. That is, could be fusing of smaller atoms together to form a big one. That's the case of the type of reaction, basically nuclear fission and nuclear fusion. But I'm interested in this because this uranium is an atom that was completely destroyed to form this. By this is some of the very base of ideas where you can do your radiocarbon datings, where you can understand how old, it as a result of the years it takes for this to transform to this. You begin to calculate how many of these years is possible, for how long has it been, for how many of the radioactive decay has it actually undergone. So that is it about some of the basic modifications. And then I wanted to also add on this modification that aside from just atoms can be created, although it works for other elements, but not categorically for, there are some peculiarity, there are some exceptions, that those exception is in the radioactive element. And then another modification is the idea of elements of the same, atoms of the same element look alike in all aspects. I think it's also a point to look into, because the idea of isotope or isotopy have actually changed, or there's a bit of contradiction in the sense that elements of atoms of same element sometimes do not look alike. Yeah, sometimes not. This is a very good situation or a case of chlorine. Okay, you have 37 and you have 17. You have chlorine 35, 17. It's an isotope, the same atomic number, a different mass number. So this is what informs it, and this result as a result of comes as a result of some of these atoms tends to have more of the neutrons in a nucleus. So when you have more of the neutron, it has more numbers of the neutrons in the nucleus, because in the nucleus the mass number of an element of an atom is decided based on the numbers of protons and neutrons. You get it now? While the atomic number is informed due to the numbers of electrons, So that is what it is about. Some of the contradictions, some of those modifications. That a lot more if you want to talk. A few more per se of this modifications, this advancement. So gradually, this is what the modern theory based on, because with time you will be seeing a lot of contributions of what an atom looks like. Everybody, a lot of scientists were struggling to find out, this is what I feel the atom looks like, this is what it is. That's what comes about the complete makeup of the knowledge we have today about atoms. People like Ernest Rutherford, J.J. Thomson, James Chadwick, so many of them. You can name as much as you can. So you see them trying to, bring about certain theories in Neil Bohr. Yes, people like Neil Bohr, people like Schrodinger, so many of them came about their own postulates and postulating what an atom really is. But today we will not be talking about what those postulates or those postulates are. Today we just took time to lay a base foundation on what an atom really is in the perspective of the modern theory, what brought about it, right from the time of the philosophers down to John Dalton in the early 19th century. So, what about the third objective, which is electronic configuration of elements in the periodic table? So, electronic configuration of elements. Let's do something little about that. Let's do something about that. Okay, on the electronic configuration element, right? Electronic configuration of element. Electronic configuration is the filling of electrons in an atom. That's just it. Either in an atom or the filling of electrons in different energy levels. Yeah. So everything about electronic configuration is either the filling or the arrangement of these electrons in an atom. That's just what electronic configuration is. How are these electrons arranged in an atom? How do we position the arrangements of these electrons? Because we said an atom is made up of the electrons in the outer shell, and then in the nucleus you find, we said an atom, the electrons, and then here, which is the nucleus, contains the proton and the neutron. So, if this is our interest today, how are these electrons arranged in an atom? That is electronic configuration. Electronic configuration can be seen either in a macroscopic, allow me to use that word, or microscopic. What I mean by macro and microscopic is there is an arrangement of these electrons according to shells. That is macro, that is the broader view of it. And there is this arrangement of electrons in the shell. It's all the same. It's all the same. It's all the same. But it's based on where, the perspective where you're looking to. If you're looking at the shells, it is more, I wouldn't say not detailed, but it is more wide and not specific. But when you talk about filling of electrons or arrangement of electrons in orbital, now you begin to go into, the lens. You're going through the lens and you're trying to magnify to find out. It's just like we said, in this is the shell where the electrons are found, but in the shell is the orbital, and in the orbital is this arrangement of electrons. So let's dive into it and see how we can share more light to this electronic configuration. So if the electrons are in the atom shell, yes, and the nucleus, they contain the proton and the neutron, we have the shells. Let's talk about the shells. Talk about the numbers of shells. Talk about maximum number of electrons. Permit me. This is electron. So in shell 1, in the first shell is the K shell. 1 is in the first number of shell, that is